Okay, well, yeah, thanks for that introduction and thanks for the invite to present to this group. I was looking through the GitHub of the previous talks, and it's really a who's who of some of the best software out there, including a couple R packages that I'm going to mention in this talk. So that's pretty cool. But today I'm going to be talking about the unmarked R package for fitting hierarchical models of animal abundance and occurrence. And this is a package I think useful to ecologists and wildlife biologists in particular. So here's an outline of what I'm going to talk about. I'm going to give a brief, maybe 10-minute overview of what I mean by hierarchical models in this context. A lot of this will probably be reviewed to many people on this call, but just to make sure everyone's on the same page, I'm going to give this brief overview. Then I'll talk about the organization of unmarked and the supported, give an overview of the supported models so you can get a sense of the span of what's possible with the package. Third, I'll do a package demonstration, so a basic workflow of one particular fitted model type. And if you want to follow along with that, all the code for it is provided on GitHub. I would recommend pulling out there's a bunch of different files there, but the one that's a .r file is probably the one you want. Since many people have probably used unmarked since it's been around for a while, I will then focus on some of the more recent features, specifically random effect support, simulation, and power analyses to give you a sense of what's been worked on recently. Then I'll talk about some future directions briefly, and finally take questions. So let's start with that overview I mentioned. In almost all cases, when we are trying to measure animal populations, we're not really able to census. So if we're trying to figure out where animals are or how many animals are present at a location, our detection is always going to be imperfect unless we've got a laboratory setting or some other kind of controlled system. And if detection is ignored, then what we're really measuring is typically a combination of the so-called state and detection processes. So what I mean by state is the true underlying abundance or occurrence of a species at a location. And so if we ignore detection, then we're mixing up those two things. And in many cases, that may not matter. For many types of inference, it might not matter. But in many cases, it might matter. For example, if certain covariates affect the detection of a species, and, for example, also affect the occupancy or abundance of that species at a site, then if we ignore detection, any inference that we make may be biased. So a solution to this problem is to use models that explicitly separate the state and detection processes. And there have been many models developed for this purpose. So the classic example, and probably the most simple example, is the occupancy model. And what I mean by occupancy here is the probability that a species is present at a site, which is kind of the fundamental ingredient of a species distribution model. So here is a diagram, a very simple diagram I made to demonstrate occupancy. So the squares at the top here represent the true underlying state of a site. The shaded square represents a site that is occupied by a species. The unshaded square is a site that is unoccupied by a species. And then as scientists, we go out and sample those sites. So on the left, we go and sample the occupied site. And on the first visit, we may find the species. On the second visit, we may not find the species, depending on how detectable it is. And then on the third visit, we may find it again. So in this case, if we only visited the site, if we only made that second visit, then we may incorrectly determine that the species is absent when it is in fact present. Then on the right-hand side, in this simple example, we have an unoccupied site, and every time we visit that site, we will find that the species is not present. So on the top, we have the occupancy or the state process, and on the bottom is the detection process. So moving on to the basic math that's represented in that diagram. First, I'll talk about the state process. The two key parameters are what is often called Z and psi. So Z sub I is the latent occupancy at site I, so the true presence or absence. And that takes on a value of 1 if the site is occupied and 0 if it's not. And then the occupancy probability psi, which is, again, the probability that the site's occupied. And that can vary between sites or it could be constant across sites. And then the simplest way this is presented in math is to have the latent occupancy modeled as a Bernoulli random variable or a coin flip with the parameter psi. And of course, psi could be modeled as a function of covariates, such as elevation or forest or whatever. And so we've got a linear predictor of some set of covariates, and then typically we use some transformation like a logit to convert that linear predictor into a probability that ranges from 0 to 1. So for the detection process, the key components are, first of all, the observed data, which is detection, non-detection data for site I at repeated sample j. So typically we have more than one site and more than one repeated sample per site. And again, these data are going to be zeros if we don't detect the species and ones if we do. And then we also have a corresponding probability of detecting a species. That should say a species, not an individual, at site I and sample j. The probability of detection could be constant across all sites, or it could vary. And then the simple math is that detection, non-detection data is modeled as a Bernoulli again, where the parameter is a product of the detection probability and the true latent state. So if the site is occupied, in truth, z sub I will be 1, and that simplifies down to y is distributed as Bernoulli with a parameter p. So it varies with the magnitude of the detection probability. On the other hand, if z sub I is 0, if the site is unoccupied, then the detection, non-detection data will always be 0. And again, this is the simplest version of the occupancy model. Other varieties are possible that relax some of these things that I've just said. So here's an example of what the data look like. And this will also more or less reflect the real data that we use later on in the example. So we've got a matrix here where the rows represent sites and the columns represent repeated sampling occasions. And each element of the matrix represents a detection event, and we get a 0 if it's a non-detection and 1 if it's a detection. So for example, in this case, on occasion 1 at site A, we did not detect the species, but at site B on occasion 1, we did detect the species. And it's also possible you might have unbalanced designs here where you have different numbers of sampling occasions per site or other types of missing data. So there's a number of key assumptions in these models. First of all, perhaps most importantly, the population has to be closed during the repeated samples. So from the first repeated sample to the last repeated sample, there can't be any birth, death, immigration, or emigration, because if that were the case, then the occupancy state would be changing between repeated samples, which is not possible, that means the state and the detection process will be mixed together and we won't be able to separate them. In reality, this is almost never true unless your sampling occasions are basically simultaneous, but you just try to get as close as you can in practice or use some other method that relaxes this assumption a bit. We assume the repeated samples are independent. We also assume there's no unmodeled heterogeneity or in occupancy or detection. So practically speaking, if there are any key covariates, we've included them in the model in some form. And also, we're assuming there are no false positive detections. So if we detect a species, then it's there. So it's not possible that we've misidentified the species or something. There are models that can handle those, but the simple one that I've just described can only handle false negatives. So you can extend this basic structure to counts as well. And we would just replace the state process with, or the state variable with some abundance or a count, which we can call n. And then instead of a Bernoulli, we can model that as a Poisson or a negative binomial with parameter lambda representing the mean abundance. And then the detection process becomes binomial with sample size equal to the true population size n, and the detection probability becomes an individual animal detection probability. And then the data are counts instead of zeros and ones. So here's an example of what that data might look like in a simple case. So instead of zeros and ones, we now have counts at each site. So that's a very brief overview of hierarchical modeling. If you're interested in this stuff in more detail, I recommend the Applied Hierarchical Modeling and Ecology volumes 1 and 2 by Marc, Kéry, and Royle, which also makes heavy use of unmarked. So now let's move on to talking more specifically about the unmarked package, which is meant to handle the model I just described and many other similar types of models. It's called the unmarked package because the model types are focused on data sets where you do not have marked animals or you have unmarked animals. So you're not, for example, individually ear tagging mice or looking at patterns of spots or something like that where you can identify individual animals. So you're just doing counts or you're just doing presence absence. If you do have marked animals, there actually are some types of models with marked animals you can fit in unmarked, but that's not the focus. So you can look at other software such as Marc, which is kind of the most famous and commonly used software for that purpose. So unmarked has been around for quite a while as an R package. It was first submitted to CRAN in 2009. And the original developers were Ian Fisk and Richard Chandler. So really, I have to give a huge amount of credit to them for building the original package and really doing most of the development work. And I think unmarked is kind of a cool example of a long-term community open source maintenance project. I mean, it's just been around for a long time and it's had multiple maintainers since it was originally developed. And it's been continually improved over that time. So here's a diagram that represents kind of my concept of the overall organization of the package that involves three questions that will help you decide which model type specifically to use within the package, since there are many, as we'll see here in a few slides. So the first question is, what metric are you trying to model? And so that would be either abundance or occupancy. Second is the temporal design. And I'll describe what I mean by that in a second. And third is the observation type. So do you have detection, non-detection data? Do you have count data, and so on? And I'll describe a few types that unmarked supports, again, in a couple slides. So the answers to these three questions will determine which model is the most appropriate. So for metric, again, the two that are the focus of unmarked are occupancy or occurrence and abundance. And these little diagrams just represent the true states of systems, the latent states. On the left, we've got a bunch of sites that are either occupied or unoccupied. And on the right, we've got a bunch of sites that have some underlying true abundance. And of course, the definition of what a site is a key question in this type of modeling, which is often very difficult. And I'm not going to get into that here, but it is something that you have to figure out for your specific experiment. So the temporal design, there are three types of temporal designs that unmarked supports. The one that's most common and is most widely supported is one primary period. So this is a typical situation where you've sampled in 1 year or one season, and you've got your set of repeated samples or the other detection options, which I'll talk about in a second. So that's the simple case and the one that's most widely supported across all the model types in unmarked. The second type is a situation where you've got, again, a single primary period, so a single year or season, but then within that, you've kind of got a robust design with multiple secondary periods. So this could be a situation where you're, for example, doing a series of 2 or 3 bird point counts 1 day apart in 1 week, and then you wait 2 weeks and you do another one, and then in 2 weeks and you do another one, or another set of 3. And so you've got like this structure where you've got some groups of sampling occasions, but they're all close enough together that you would consider them to be 1 year or one season. And if you have that type of structure, you can model it explicitly, and that allows you to estimate additional parameters like availability or handling situations like temporary emigration. And then finally, we've got multiple primary periods, and this would be classically multiple years of data at the same sites where you want to measure things like colonization, extinction, or emigration and emigration. So the final question is what type of data you have. And unmarked supports a variety of different data types. That's probably its biggest strength. And so you could have detection, non-detection data, which we've already discussed. You could have repeated count data, which we've discussed. You could have time to detection, which is basically you go out to a site and you sit there until and start your stopwatch and you wait until you detect a species, for example, here a bird call. And the length of time that it takes you to detect that species tells you something about how easy it is to detect. Unmarked also supports a variety of distance sampling models where you go out, for example, on a transect and you look on either side of the transect and you measure how far away you see individuals. And that tells you something about how detectable those species are. There's also removal sampling, double observer sampling, and other types of multinomial structures. So, assuming that occupancy modeling is what you want, I've created a table here that tells you, based on what data type you have and what type of temporal design you have, what the most appropriate unmarked model will be. So each unmarked model corresponds to one specific, what we call fitting function, which have names that are vaguely informative, I would say. They're not the best. So that's why tables like this are helpful. But you can see in the rows here, we've got different data types. So that includes things like having multiple species. Maybe you're interested in species interactions or you have false positives. Maybe you've got more than two possible states. So instead of just presence and absence, you also have something like absence, presence but no reproduction, and presence with reproduction. And then time to detection or count data. And then across the top, we've got these different temporal designs that I described. So if you pick your data type and pick your primary or your temporal design, then you can see if that model is available and unmarked. And many of them are, but some of them, as you can see, are not. And just to highlight a few that have been added in the past couple of years, the OccuCom function is a function for the community occupancy model, where you're wanting to model multiple species simultaneously, and those species, the effects of covariates and so on for those species are basically treated as random effects. Also recently added was the GOCU function, where you you can handle temporary immigration or multiple data types. And then the OccuCop function is handy for when you want to estimate occupancy, but you have count data, which is pretty common from something like camera trap data. And as you can see, there tends to be less good support for the more complex temporal structures. Someday we'd like to fill in those gaps. We'll see if it ever happens, though. So if you're interested in abundance, then here's a similar type of table. And again, there's a bunch of different data types. Once you get into abundance models, then we also have distance sampling and then other multinomial types like double observer or removal sampling. One kind of interesting one that's been added recently is a combination of distance and removal data. So this is actually pretty common for bird point counts, where you are doing a point count, and every time you see a bird, you both measure or estimate the distance to that bird and then also which time bin it fell into. So if you have both of those things, that allows you to get better estimates of detection and also estimate availability, among other things. And then you can also get abundance from time to detection data, which is kind of neat. So we've got a little bit better support for multiple secondary and multiple primary periods for the abundance models as well. So that's the basic organization of Unmarked. So now I'm going to do a simple demonstration of the package. So just a basic workflow from more or less start to finish. And again, I'm just going to do it on a basic single season occupancy model so that the focus is on the structure of Unmarked and not so much on the complexity of the model, because some of the other models can be much more complicated to implement. So the basic workflow, which could include other things depending on what you're trying to do, is first of all, to format the input data, to read it in and format it in the structure Unmarked wants, then to fit a model or several models depending on your goals. Then you might want to look at goodness of fit, which Unmarked includes a few tools to help you with that. And then finally, you might want to do different kinds of prediction. So in this talk, rather than swapping back and forth between the presentation and an R console or R Studio or something, I'm going to be running the code directly in this presentation, which is actually a Jupyter notebook. So these code boxes are going to pop up, and I'll try to make sure that they're as big as possible so you can read the code and the output. So what I read in here is going to be, it's going to look a little different than what you're doing if you're following along in RStudio or something, but the outputs should be the same. So the first step is to load the unmarked library. And again, if you want to follow along, you can pull that out of the GitHub folder. So I'm going to be working with this data set of this bird, a crossbill, which is found in Switzerland. I don't know much about it, to be honest, but it's a data set that's kind of neat and usable for a bunch of different model types. And it's built into unmarked, so everyone has access to the full data set. I've actually pulled out the version in unmarked and broken it up into a series of CSV files so that we can kind of show the full workflow from what you do if you you had your own data. But if you want to see the original data set, which includes some information that I haven't included in the example, then you can look at the help file for the crossbill function, or the crossbill data set in unmarked, which has a full explanation. So let's first read in the detection, non-detection data for crossbills. And we usually call this data Y in unmarked. I mean, that's pretty typical for all linear models, I guess. So I'm going to make an object called Y, and I'm going to read in with read.csv the Y.csv function. So that's in the data subfolder in the GitHub repository. So in order for this code to work, you need to set your working directory to the main GitHub repository, or the my specific folder in the GitHub repository. So the Kellner-unmarked folder. And then that should allow us to read in this y.csv file that's in the data subfolder. Then I'm going to look at the dimensions of the output as well as the first few rows so that you can see what we've got. So this object has 801 rows and 3 columns, and you can see the first 6 rows below. Each row here represents a site, and each column represents a repeated sampling occasion. And this is the exact structure that unmarked wants, and is, I would say, the typical way, or one of the 2 typical ways that these data are usually recorded. The other one being each row representing a single sampling occasion. And if you have data like that, you'll have to reorganize it into a matrix like this one, where you've got each row as a site and each column as a sampling occasion. So I guess you could call that the wide format. We also have some covariates, and those are contained in this file in the data subfolder called site_coves.csv. So I'm going to read that function, or that folder, I'm sorry, that data set in as an object called site_coves, and then again, look at the dimensions and the first few rows. So again, this data frame is going to have 801 rows in 3 columns. So the 801 rows again correspond to the 801 sites, but the 3 columns are now 3 separate site level covariates. So we've got site ID, which we're not going to work with here, but we will work with later on in the presentation. And then forest cover as an integer, and elevation. And I believe that the original crossbill data set also includes some other covariates, which I haven't included here. So this data frame should have the same number of rows as the number of sites, but it could have an arbitrary number of columns depending on how many covariates you have. So we could also have observation level covariates. So the site level covariates, there's just a single value per site. So again, it would be things like forest or elevation that aren't changing throughout the study, or at least not within years. We could have observation level covariates where the covariate value is changing across both sites and sampling occasions. So this would be something like weather, precipitation or temperature that vary between both site and occasion, or something like observation date as an ordinal number. And indeed, that is what we have. So there's another file called dates.csv in the data subfolder, and this contains the ordinal date of each sampling occasion at each site. So I'm going to read that in and take a look at it. So this object has, again, 801 rows and 3 columns. And here are the first 6 rows. And the dimensions of all your observation covariates should match exactly the dimensions of your detection, non-detection data, because each cell in this matrix corresponds to one cell in the detection, non-detection matrix. So for example, the first row, first column is 34, which is the ordinal date of the first detection, non-detection value at site 1. And I should have mentioned when I looked at Y, so I'll go back to it really quick. You'll notice that for the third site, both here and in the observation data, we've got all missing values. And that's just because this cross-build data set is quite messy, and it includes some sites where for whatever reason it was included, even though it wasn't actually measured. And that's fine. Unmarked handles those things just fine automatically. You could also have a scenario where, some values in a row are NAs, but the other ones are not. And that would represent a scenario where, at that site, you only measured it once instead of 3 times, and that's just fine. Unmarked can handle that automatically. Unbalanced designs are very common in these types of studies. So we wanted to make sure to support that type of situation. So again, you can see the missing values in the observed data here as well. Or I'm sorry, the observation covariate. So the next step, once all that data is read in, and actually, yeah, no, I did read it in, is to create what we call an unmarked frame. And this is basically unmarked's equivalent to ours data frame concept. And the point of the data frame, I guess, or one of the points of the data frame is that it contains all the information you need, to run some model. And that's what the unmarked frame is as well. It's one object in R that contains all the information about the experimental design that you need to fit the model, as well as all the covariate data and the response data. And in creating that object, a bunch of tests are run to make sure that everything matches. So make sure you have the right number of rows and columns for everything, and so on. For this simple model, it doesn't matter as much, but for some of the more complex models, it can be hard to get all the bookkeeping right. And so the unmarked frames are a way of checking that before you actually run the models. So each unmarked fit type, which are those functions that I showed in those previous 2 tables, each one tends to have its own specific unmarked frame type, since every model requires different design elements. And they tend to have names that try to match more or less the fitting function name. So we're going to fit the single species occupancy model, which is the occu function. And so the unmarked frame type is called an unmarked frame occu, which is kind of long and clunky, but at least the name matches. So we're going to call the unmarked frame occu function and save the output into an object called UMF. And for this simple model, we just have 3 pieces of information. We have Y, our matrix of detection, non-detection data. We have site coves, note the camel case here, which is our data frame of site level covariates. And we have our obs coves, which is the observation covariates. And these are a little trickier. You need to provide them as a named R list, where each list element is a matrix with the same dimensions as the detection, non-detection data. So remember, the date matrix had the exact same dimensions as Y because the cells corresponded to each other exactly. So here we've got an R list with one element because we only have one observation covariate, and that element is called date, and that list slot is filled up with the date matrix. So the observation covariates can be a little bit trickier, but in this case, with just one, it's not too bad. So if we then look at if we call head on that output object, it'll show us kind of a flattened representation of the unmarked frame. And it will also perform a bunch of checks in the background to make sure everything matches up. So if you get an error or a warning here, you should pay close attention to it, and use that to help you fix any issues. So this just shows us all the information we provided in kind of a flattened format. The first few columns are the detection, non-detection data. Then we've got the site covariates. Then we've got the observation covariates. So with the data organized, we can now actually fit a model. And unmarked uses our formulas to define the model structure, much like if you've used the LM function for basic linear regressions, or the GLM function for generalized linear modeling, or the LME4 or GLMM-TMB package for mixed modeling, and many, many other R packages that use our formulas. This should be familiar to you. One thing that unmarked adds is these double formulas, because remember, for hierarchical models, we've got 2 or more processes that we're modeling, what I call submodels. So we've got, in the specific case of the single species occupancy model, we've got the detection process and the occupancy process. And each of those is its own model that could have its own covariates that could differ. So we actually need to provide 2 formulas in this case. And the way that unmarked does this is you provided a double formula. So you can see there's 2 tildes in here. The first formula is the detection formula, and the second one is the state formula or the occupancy formula. And notice there's no comma or plus sign or anything between these two formulas. So it's one object. And if you had different covariates on detection, you put them here. If you had occupancy covariates, you put them here. Unfortunately, unmarked is not super consistent about the use of this double formula. The example we'll look at uses it, but other types of more complicated models actually just have separate arguments for each submodel formula, which is in some ways easier. So you kind of just have to look at the documentation to figure out how it should be specified. So let's fit a null model to start with, and we'll call that mod underscore null. And so the first argument to the occu function, which is what we use to fit this model, is our double formula. And again, because this is a null or intercept only model, both component formulas here are just tilde1 for intercept only. And then the only other argument we need to provide is the unmarked frame, because that contains all the experimental design and covariate information. Some other more complex model types may require other arguments here. Like, for example, if you're fitting an abundance model, there may be an argument to specify if you want to fit a Poisson abundance model or a negative binomial abundance submodel. So let's fit that model and then take a look at the summary. And unmarked uses maximum likelihood under the hood using Optim in R. And so it's quite fast for the most part. And so I'll now just describe a few of the things you see in the output here. First of all, we get a warning. And this just tells us that we had a bunch of sites with missing values, which we saw earlier on. For example, site 3. And those sites are dropped during estimation because they're not providing any useful information. You should always pay close attention to these warnings because it's possible that if you misspecify something in the unmarked frame and it isn't caught by the unmarked frame, then you may end up with a situation where you have a site that has missing data, but you didn't mean for it to be missing. So you should just always double check when you get a warning message like this to make sure it's what you expect. You may also get some warnings if the output is questionable for various reasons. Like if it looks like the optimization in the background didn't work properly or it didn't converge or something. So definitely always pay attention to those warnings. So in the output here, we first just get a repeat back to us of what the code that we used to call the model was. And then we get two tables, one per submodel, that contain the parameter estimates and z-scores and p-values. And these estimates are on the transformed scale. So recall back, I said that when you do the linear predictor for occupancy, you then transform that with a logit to convert it into a probability. So these numbers are on the logit scale. And a common mistake people make is to think that these estimates are actual estimates of occupancy, like their probabilities. In this specific case, we know that's not true because we can't have a negative occupancy probability. But sometimes, like with the detection value here, that looks like it could be a probability. So, up here, you're reminded that these are on the logit scale. And you need to transform them if you want actual probabilities. You also get an AIC score, among other things. And because this is a null model, we just get a single parameter estimate for each submodel corresponding to the intercept. So in this simple case, you can just quickly back transform these numbers to get actual probabilities using the plogis function in R. And so it turns out that we have an estimated occupancy of about 0.31 and an estimated detection of about 0.55. Obviously, if you had covariates, it wouldn't be quite this simple, as we'll see here in a minute. And there are other ways built into unmarked for doing the same process. So now let's move on to a covariate model, since that's what most people end up doing eventually. We'll model detection as a function of ordinal date, which is our observation covariate, the only one we've got. And we'll model occupancy as a function of forest and elevation. So the formula becomes forest plus LE. So here's what the full double formula looks like in that case. Remember, the detection formula is first and the occupancy formula is second. So we'll create an object called mod underscore coves, and everything's the same except we've changed the formula. And notice also that I have made an additional modification to the formula, which is that I've wrapped all the covariates in the scale function. So if you're not familiar with it, in R, the scale function takes any vector and converts the values to have a mean of 0 and a standard deviation of 1. So it turns it into a z-score. And that's really handy for a couple reasons. For certain models and certain covariate values, if the covariate values are really, really big, like thousands or even hundreds in some cases, the underlying optimization that unmarked is doing can choke and struggle and not converge, because it kind of wants values that are close to 0 in most cases. So if you scale those covariates, then the optimization may work much better. And also, if you scale the covariates, that makes the parameter estimates you get a little more directly comparable. My recommendation is to always scale the covariates when you're using unmarked, unless you have a good reason not to. And you could just scale them manually before you put the covariates into the unmarked frame. That's totally fine. You just have to remember how you scaled them if you then do some prediction later on. But you can also put scale right into the formulas here, which will do it automatically. And you can also use other functions in the formulas, like the I function, which allows you to do, for example, quadratic stuff or polynomials or whatever. There's some limitations there, but for the most part, most things should work the same way they would if you're using, for example, LM or GLM. So let's take a look at the output from this model. We get the same warning. And now we have output that includes both intercepts and slopes for the coefficients or for the parameters included in each submodel. So it looks like for this simple model, we've got a pretty strong positive effect of forest and elevation on crossbill occupancy. That's what we'd conclude looking at this. And then it looks like date has a positive effect on detection probability. So of course, if you're doing this for real, you'd want to perhaps look into quadratic effects or something else, depending on what you understood about the system or what your hypotheses were. And you can also do model selection. I don't show that here, but there's basic tools for that as well, to compare AIC scores. So next I wanted to talk a little bit about goodness of fit and unmarked. This is something of a challenge with hierarchical models in the sense that they don't tend to have great, there don't tend to be available a lot of great purpose-built fit statistics, at least that I'm aware of. So things are a bit limited, but unmarked has a built-in tool for parametric bootstrapping, which can be useful for goodness of fit and a bunch of other tasks as well. The basic idea here is that you find some fit statistic, which again is often a challenge, finding an appropriate one, and you apply it to your model. But that single number doesn't typically tell you much. And so what you can do is you can simulate a bunch of quote unquote perfect data sets based on your model. And I say perfect because you're simulating them from the fitted model, and therefore they should fit perfectly. You then fit models to these perfect data sets and apply the fit statistic to those ones as well. And that will give you a complete distribution of fit statistics for quote unquote perfect data sets. And then you compare your real fit statistic to that distribution. Hopefully it falls in that distribution, near the center of that distribution. And that tells you, at least that gives you some evidence that there isn't, a major issue with fit. So unmarked, that could be a lot of work to do manually. So unmarked has built-in tools for it. So I'm going to set a random seed for reproducibility here. And then I'm going to run the built-in function parboot. And I'm going to call that on the fitted model with covariates. And I'm going to specify how many simulations I'm going to do. In this case, 30. In reality, you should do a lot more, but of course it takes longer the more simulations you use. And then what I haven't specified here is what fit statistic to use. So it's just going to use the default one, which is the sum of squared residuals, it is what it is. It's not ideal, but that's what the default is. If you come up with a better one, you can use that. And then I've just wrapped this all in suppressed warnings because there's missing values, it just will, every time it simulates the data set, it's going to complain about missing values and fill up the console output here. So I'm going to suppress those. This takes a second because it's fitting and simulating 30 data sets. But here's what a plot of the output looks like. So the histogram here represents the distribution of quote unquote perfect data sets or fit statistics for the perfect data sets. and the dotted vertical line represents the real data set, which in this case falls right in the middle of the histogram. And that's evidence that things seem to be okay fit-wise. But again, I wouldn't necessarily rely solely on this. And because it's fairly crude and the fit statistic isn't ideal. By the same token, I wouldn't, if it didn't fit, I wouldn't necessarily just discard the model. Again, it's a big challenge with these hierarchical models. There's no great solution. The book I mentioned earlier, Applied Hierarchical Modeling and Ecology, has a couple sections that go into this in more detail, but it is definitely a big challenge in these types of models that probably needs more research, and is something that I'd like to support better in the package. So there's also for the single single season occupancy model in particular, there's this other fit statistic called the McKenzie-Bailey chi-square, which is designed for occupancy models. Unmarked doesn't support it, but it's included in this really cool package, AICC mod average, which does a whole bunch of different stuff. But this statistic basically looks at the expected and observed frequencies of different encounter histories in a model. So thinking back to our detection, non-detection matrix, we had, at site 1, 0, 0, 0, at site 2, 0, 0, 1, at site 3, 1, 0, 1, or whatever. And the incidence of those different unique encounter histories can be used to assess fit. It does work well in some cases. In other cases, when you've got tons of sampling occasions, like 30 or 50 sampling occasions, or you've got tons of missing values, it starts to break down a little bit and doesn't work super well, but in some cases it can be good. And here's what the name of the function is. I'm not going to demonstrate it here, but if you're interested, go check it out. And this package also includes some fit statistics that are specific to certain abundance models that Unmarked supports as well. So it's a nice companion package. It also has a bunch of other AIC-based tools, as I mentioned. So the fourth thing I'll talk about in this workflow is prediction, which is often what you end up wanting these models for, especially if you're doing like species distribution modeling, for example. So if you want to just get an estimate of occupancy at each site, you can do that with the predict function, which I'm going to call here and I'll save the output in an object called PR. So I'll call that on my fitted model with covariates. And because I have got two submodels here, one for occupancy and one for detection, I've got to specify which one I'm predicting for. And so I'm going to say type equals state. And one unfortunate thing about unmarked is that it can be quite inconsistent about what it calls each submodel. I'm calling it the occupancy submodel, but it's also the state submodel. And here we need to specify type equals state. Sometimes it will also require you to call it by the parameter name. So psi. So it could be occupancy, state, or psi. And it's just a little bit inconsistent depending on which type of model. And you just have to look at the documentation to help with that, which is unfortunate, but it is what it is. So if we run this, we get a data frame where each row represents one site with the predicted occupancy, as well as lower and upper bounds, which are by default 95% confidence intervals. I would just ignore the standard error there. I don't think it's actually useful for anything. You can specify how big you want the confidence interval to be as another argument to predict, but by default, it's just the 95%. You can also predict for arbitrary values of covariates with new data, and that should be familiar to you if you've done this with LM or GLM. It's the same idea. So we create a data frame which contains values for all the covariates in one particular submodel. So our occupancy submodel included covariates for elevation and forest. So we create a data frame with some arbitrary values for each of them that we want to predict for example, an elevation of 500 and a forest cover of 10. And we need to have the names in this data frame, the column names exactly match the names of the covariates as they occur in the model. And again, the other thing is to make sure you need to include values for all covariates in that submodel. Those are the two mistakes I see people make. The other thing is, notice here that these covariate values are on the original scale, not the standardized scale. So elevation 500 and forest equals 10. Even though the model we fit used the scale covariates, Unmarked will handle all that in the background for you because you put scale in the formula. So it will figure out that it needs to take these values and scale them according to the means and standard deviations of the original data set. And it does all that stuff automatically. That's the drawback if you scale your covariates manually before you put them in the unmarked frame. Then later on, if you're doing this prediction with new data, you need to make sure that you scale elevation and forests according to the means and the standard deviations of the original data set. And that's a mistake I see people often make, is not doing that scaling correctly. So that's why putting scale in the formulas is nice, because it prevents accidentally making those mistakes. So then all we do is we just add this new data frame as an additional argument to predict. And we now just have a single value in the output, which corresponds to the values that we specified. And we could have a new data frame that's got multiple rows for if we have multiple sites we're interested in, multiple new sites. And a typical task that you would use this for is if you want to build kind of an effects plot where you look at the effect of a single covariate holding all the other covariates constant. Call that an effects plot, or sometimes a marginal effects plot. So you might make a sequence of elevation values and hold forest constant at some value and get a bunch of values for those and then plot them. So I'm not going to show doing that manually, but unmarked actually has a function built in for making that specific kind of plot automatically, which is called plot effects. So if we run that on our fitted model, we specify that we want type equals state for occupancy, and then we specify what covariate we want to plot. And in this case, we'll plot elevation and hold all the other covariates constant. So if we run that, we get this curve where we've got elevation. Sorry, that's kind of small. Elevation on the x-axis, and by default, the sequence is just the range of observed elevation values. And then on the y-axis is the predicted occupancy. So this just helps you visualize how that pattern occurs, and you can see it's a big positive relationship. And in the background, all the other covariates are being held at their median values if they're continuous, and their reference levels if there are factors or categorical variables. So you could use this in a publication type plot, but probably it would be more likely to be used just for quick diagnostics. There's also support for maps or for raster data. And conveniently, we have corresponding data for the crossbill data set for all of Switzerland. So I'm going to load the Terra library, which is for raster processing, and then the Switzerland data set, which is included with unmarked. Notice the capital S here. And then I will convert the Switzerland data set into a rast. I forget what the object's actually called, but the function's called rast, which will convert it into a Terra object. And then, so that output raster is going to have multiple layers because there's multiple covariates included with it. And we need to rename those layers to match the names in our original model. So that's what I'm doing in this step. I'm renaming the layers to elevation, forest, and water, or more specifically LE forest and water. These two, notice the names correspond to the names in our model, which is required. There's also this water layer, which we're not using, but we put it in there anyway. Then we can plot that. And you can see we've got layers for each of these covariates across all of Switzerland. So this, if we have these values, we can plug them into the model and get a distribution map of occupancy across all of Switzerland, which is what I'll do now. So the only additional thing we need to do here is we just need to provide that raster that we made as new data. So instead of a data frame, we're now providing it as a raster. And then if unmarked sees that there's a raster in the new data, it will do the predictions for each cell of that raster and then turn the output itself into a raster. And of course, this takes a second because there's a bunch of cells to do the prediction for. But now we've got a raster that includes, so this one is the predicted occupancy across the whole area of Switzerland. And then we also have the lower and upper bounds for the 95% confidence interval. So of course you could do this manually, but it is handy to be able to do it quickly with predict. So that's a basic workflow. It gives you an idea of the types of things you can do with an unmarked model from start to finish. And there are other things, as I mentioned, like model selection. There's also some support for cross-validation, which might be useful in different situations. There's a bunch of other types of plots you can make in some cases. And other specific model types may have other types of things you can do in the output, depending on their goals. And in general, there's pretty good documentation for all those features. Now I want to focus a little bit on a few recent features and just highlight them because you might not have if you've used unmarked in the past, you may not have seen these recent additions. I'll start with random effects support, which unmarked has at least partial support for now. This was probably the most requested feature for years. And now, thanks to the awesomeness that is Template Model Builder, or TMB, which I believe there was a previous talk on in this series, unmarked does support random effects for some model types and hopefully more later. And the cross-build data set actually contains repeated observations of the same sites. And that information is expressed in the ID column, which we haven't talked about yet. So you could, I mean, that is problematic in a sense because I forget exactly how many repeats it is, but maybe like 5. Each site is repeated in the data set like 5 times. And so we've got like a degree of pseudo replication here, right? And you could do a dynamic model, or you could try to account for that pseudo replication using, for example, a random site level intercept and or slope. So that's what I'm going to demonstrate here, just as a simple example. And the idea here is that you basically have a bunch of site-specific intercepts, which are now modeled as coming from a normal distribution with some overall mean across all the sites and some standard deviation, which is what we're going to try to estimate. Let's look again at our unmarked frame. And here's the key variable here, which is ID. And these are all unique values, but that's just because we're looking at only the first 6 sites. One thing that's a little bit annoying is that ID is a number. And we need, if to treat this as a grouping factor for random effects, we need it to be an R factor, and R is going to treat it as numeric unless we explicitly tell it to be a factor. So that's what I'm going to do here. I'm going to go back to our data frame of site covariates and convert ID into a factor manually, and then plug that back into the unmarked frame. You don't have to do this if the ID variable, or if you're using some other categorical covariate. If that's represented as a string or already as a factor, that's fine. It's just in this specific case, because it's a number, we have to make sure to tell R it's a factor. So the random effects are specified using an LME4 or GLMM TMB based syntax, which many of you may be familiar with. I feel like that's probably the most common way that this type of structure is defined across R packages. And here I have to shout out the really amazing reformulas package that Ben Volker wrote, which broke out a lot of the like background processing for handling these types of formulas and generating the giant random effects matrices. And unmarked uses that functionality in reformula so that I don't have to do all this careful bookkeeping myself. It's a gigantic help, and that package is great if you are doing something similar in one of your own packages, so I recommend it. So in this case, for example, a random intercept by site ID would be specified as open parentheses 1 for intercept, and then this vertical bar, which I think of as in my head as random by or grouped by ID, which is the grouping factor we're interested in, and then close parentheses. And if you had random slopes, they'd fall somewhere in here. And probably we should have random slopes in this example, but I'm not going to do that just for the sake of time. So I'll make a new model called mod_rand, and then the only change I've made to the formula is to add at the end here that parentheses 1 vertical bar ID. And then we'll look at the summary. This takes a bit longer to fit. So the output should look similar. And if there is a random effect in your formula, the model will automatically be sent to Template Model Builder for processing. I probably should have mentioned earlier, by default, most models are fit using a likelihood function that's written in C++ using RCPP. So it's quite fast in most cases. But if you specify a random effect, it will be sent over to TMB instead, which is still quite fast. And in the future, we may eventually move everything over to TMB because it's just a lot easier to write likelihood functions for it. We'll see if we ever get there. So in the output, the only thing that's been added here is an estimate of the random effect standard deviation, which is in this subtable right here. So it tells us what the grouping factor is, ID, what the parameter is that's random, intercept, and then the variance and the standard deviation. These are actually more or less the same number. So the variance is just the value of standard deviation squared. And the only reason I have both of these in here, even though they're kind of duplicating each other, is just I'm trying to match the structure of the LME4 output, which looks like this, more or less. So that's the estimate of that standard deviation. And the random effect in this case is all the random effects you'll estimate are assumed to be mean 0. So I think that's, oh yeah, so you can also get out the values of the individual site level random intercepts if you want. And the function for that is random terms. So if we look at the output from that, or at least the first few rows, we get for example, site one, the random intercept is negative 0.07. And also we get a confidence interval for that, which is very wide because we don't have that much data. There's only a few replicates for each site. You might think if you're very familiar with LME4 or GLMMTMB that this output really you should be obtaining it with a function called ranf. And the reason that unmarked doesn't use ranf is because ranf was already used by unmarked for a different purpose. And so I couldn't use it for also getting these values. So I had to make a new function basically. So that's why, in case you were wondering. So that's a very brief overview of random effects. Obviously, properly using random effects that could be its own presentation. And not all models support them, and not all complex random effect structures are supported. But the most basic simple stuff is supported, and the models that are supported are generally the single season models. We hope to support more later on if we get to it. So for the next thing, I'll look at simulation. And I'll move through the next two examples fairly quickly since I see I'm getting a little bit close to my hour-long allotted time here. Simulation can be super useful for creating teaching examples, exploring experimental designs, bootstrapping, goodness of fit, which we already showed, power analysis, which I'll show in more detail in a minute. So Unmarked includes a tool for simulating basically any type of data that it has a model for from scratch, which for simple models, it's pretty easy to do manually, but for more complex models, it might be hard to get all the math right. So basically, our first step is to define the experimental design. So I'm going to set a random seed here and I'm going to do a single season occupancy model with 100 sites and 3 replicate samples. And I'll create a blank matrix that just has NAs in it as sort of a structure that tells Unmarked what the structure of the design of the experiment is. Then, because I want to simulate based on a covariate, I'm going to simulate values for a covariate from a random normal distribution and put those into a data frame. So I need a value for this covariate I'm calling forest for each site. Now I'm going to build an unmarked frame, which doesn't contain any actual detection, non-detection data. It's still blank, but we put that blank matrix in as well as that simulated covariate. Here's what it looks like. We've got those blank NAs. Because we're simulating, we need to specify what the values for the coefficients should be. How big should occupancy be? How big should detection should be? What's the effect of the covariate? And these parameter estimates should be on the link scale, which can be a little bit tricky. And they need to be provided in a list for each submodel. So here's an example of that structure. So we've got a list with one element called state and one element called det corresponding to the state and det submodels. So for state, we're going to have a model with an intercept and an effective forest. So here's the intercept value and here's the covariate effect. And then for detection, it's just going to be intercept only. So here's the detection intercept 0.2. And if we back transform those intercepts just to give us a sense of what we're actually simulating here, it's an average occupancy of about 0.18 and an average detection of about 0.55. But pick whatever values make sense for the simulation you're doing. So to run simulate, we provide this experimental design, the name of the model we want to simulate from, which will be OCU, the model structure as a formula, the coefficient parameter values, which we just created, and then however many data sets we want to make. It could be 1, it could be 100. So here's the call to simulate. We have our blank unmarked frame. We have OCU, the name of the model we're simulating from. Here's the model defined as a formula. So it's the intercept only for detection and effective forest for occupancy. Here's that list of coefficient values. And then we say we want 3 simulations. And we'll look at just the first output element. So here's one new data set that we created. And you can see now that Y matrix has been filled in with detection, non-detection data sets. And if we fit a model to that simulated data set, we should get parameter estimates that are pretty similar to the real ones that we specified. In this case, they are. Remember, the real value for the intercept was negative 1.5, and the value for forest was 1. So these are pretty close. And if you did a whole bunch of simulations and average them together, you'd get values very close to the real values. So that's simulation. Now I'll talk about power analysis, which is based on the simulation tools. So a very quick overview of power analysis. We've got type 1 and type 2 error, and then power is 1 minus the type 2 error. And we want large power when we're doing significance testing. And it's the probability that we reject a null hypothesis when it's false. What affects power? The more sample size, the more power. And the bigger the effect size you're interested in, the more power, as well as the choice of alpha. And I'm going to focus here on the effective sample size. So in hierarchical modeling, lots and lots of papers, especially the ones using unmarked, use significance testing versus some other like more Bayesian approach, for example, that looks at credible intervals or whatever. However, you almost never see anybody do power analyses. And in general, hierarchical models require, I would say, larger or much larger sample sizes than equivalent regression type models that don't have this hierarchical structure. Because they're more complicated, they've got more parameters and so on. It makes sense. The other problem is that there aren't generally closed form power equations for hierarchical models. For lots of analysis types, you have some equation or tool that you can get power from very easily for linear regression or ANOVAs or t-tests or whatever. But for complex hierarchical models, there aren't these tools available. There actually happens to be one. There's a cool paper that does it for simple occupancy models. But for these other papers or these other models, there tends to not be. And so one way to do this is using simulation, where you just simulate a whole bunch of data sets based on some particular effect size, and then determine the proportion of those simulated model data sets and model fits that detected the effect. And that's what the power analysis function does using simulation. And again, it's basically all the same arguments that we required for simulation. Instead of coefficient values, it's now the effect sizes that we want to specify. So starting off, we had 100 sites. And the power analysis function, we need to provide the experimental design, the model we're interested in, the model structure. So again, it'll be intercept only for detection and forest as the only occupancy covariate. And then the effects, we're going to just use those same parameter values that we specified earlier. And then finally, we need to specify the number of simulations, which I'm going to set to 100 here, but it should probably be more than that in reality. And if we look at that, we get a nice little output that tells us what the power is to detect an effect size of 1 for this forest covariate. And we have quite a bit of power, actually, nearly 0.9. And we're going to ignore these two things for now. I'll talk about them more in a second. So we may want to compare the number of sites. We may want to compare power for number of sites. So all I'm going to do is rerun that same code, but I'm going to change the number of sites in the experimental design object. So you can bracket an unmarked frame object, which is what I do here, and say, I just want the first 50 sites of this object. And then here I said, I just want the first 25 sites. And so this will be a power analysis with 50 sites, and this will be a power analysis with 25 sites. We're going to get a warning here. Maybe. Yeah, so R had a bit of trouble with optimization, probably from these 25 site models, because that's just way too small of a sample size. I'm just going to ignore that for now, but if you're doing this in reality, you would want to pay attention to that. So looking at the 50 site power analysis, you can see that we only have power 0.4, which is pretty low. And you can see that our type M error is 1.8. So type S error is the probability of getting a significant effect with the wrong sign. Here it's 0, which is fine. I'm not going to talk more about type S error here. There's an Andrew Gelman paper that covers this stuff, which is pretty interesting. For type M error, it's a measure of the effect size magnitude relative to the truth. So the basic idea is that if you've got low power, but you still you happen to detect a significant effect in your actual realized study, it's likely that that effect size is probably much larger than it is in reality, which is obviously a problem. So to illustrate this, if we plot the output from the 50 site power analysis, each of these dots represents one of the 100 simulations. The gray dots are simulations where we did not have a significant effective forest, and the red dots are the ones where we did have a significant effective forest. The black dotted line represents the true effect size. You'll notice that the mean effect size for only those simulations where we had a significant effect, the average is like almost twice the true effect size. So if you had low power, but you happen to detect a significant effect in your real study, chances are your effect size is bigger than the real one, which is obviously a problem. You can also compare these different power analyses if we put them into an unmarked power list. So that just gives us basically a combination of the results from before. More interestingly, you can plot them and specify some target power, and that will create the classic power plot you're probably familiar with, where this dotted line represents the target power. And as we increase the number of sites, our power increases. You could also have specified different numbers of observations, and that could affect the power as well. And if you were doing this for real, you'd want to have more different, numbers of sites so that you could get a nice cleaner curve. So that's power analysis. Future directions, we want to handle AI, output from AI tools like Wildlife Insights, ARUs, camera traps, a little more directly. More collaboration with other R packages, especially those associated with hierarchical modeling. In particular, I'll call out Jeff Dozier's SP occupancy and SP abundance packages, which were a previous talk in this seminar series. And then also, I've got some ideas for cool Nimble stuff that I want to do with Unmarked. Nimble was also a previous talk in this series. I want to expand random effect support. And as far as model types, I want to do continuous time detection models. And we've started kind of working on that a little bit. And then finally, long-term maintenance is my most important goal, to make sure that Unmarked continues forward into the future. So with that, I'll just highlight a few more resources if you're interested in them. There's also a previous seminar on Unmarked in this series on one specific model type, the multi-species model, which you might be interested in. You can email me if you have questions. And also, I'm right now at the Wildlife Society meeting in Edmonton. So if you happen to be there, come seek me out.
Thank you so much, Ken. We have two questions on the poll everywhere. Let's see. First
I'm
question.
going to
Uh,
turn off my screen share here so I can see them.
okay. So the first question is, what would cause a data set not to fit within a bootstrapped goodness fit, and what should one look out for if the original data is not supported by the bootstrapped version?
Yeah, so I mean, probably the uh, most common thing that happens is when you're doing an abundance model and you have and by default, the abundance models tend to use a Poisson distribution uh, for the model structure. And most people probably know, in reality, almost nothing is ever distributed Poisson in the real world. There's zero inflation or some other degree of over dispersion. And if you don't account for that, then you will get poor goodness of fit in most cases. Another common reason for it would be that there's some key covariate that you have not captured, you've not included in your model type. That's really important. And if you don't include that, sometimes the fit will look really bad. Another thing is just simply that your data set is very small relative to what's needed for these models. I think people tend to underestimate the amount of data that is typically needed even for a simple occupancy model. And if you have a very small data set, then fit may look like it's quite bad. As I mentioned, however, though, you shouldn't necessarily discard a model just because it seems to fit poorly, because there just aren't really great, perfect fit statistics for these models, in my opinion. And so you just kind of have to take it as one ingredient in your decision about how to use a model. In particular, one thing we've often noticed is that for count models, you may find that negative binomial models, for example, tend to fit better based on the fit statistics you're using, but they give much worse predictions, which is, in my opinion, you might want better predictions. I mean, that might be more important in a lot of cases than getting perfect goodness of fit. It's a big, tough question that I don't have necessarily great answers for. So yeah, hopefully that was helpful. I see there's another question in the poll. Should I just jump right to that one?
Yes, if you can read the question yourself and then answer, that'd be perfect.
Okay, so how does one troubleshoot warnings that the Hessian did not converge? This happened for me in cases with large or very small number of detections. Is there an ideal proportion of detections that would make occupancy models ideal when working with edge cases? That's another very hard question. Yeah, so troubleshooting the warnings. I would say that you've pinpointed in your question the by far most common reason for that to happen, which is that you just don't have enough data. So it could be that you don't have enough detections. It could also be, as I mentioned earlier, that you do not have enough sites, which is kind of a separate issue, or not enough occasions, or you may have a lot of detections, but you never um, detect species multiple times at the same sites. So, for example, you detect a species at almost all sites, but only in the first sampling occasion and never again after that, right? That makes detection almost impossible to estimate in most cases, which will cause troubleshooting, cause warnings with the Hessian. And I would say that sometimes you can fix these issues using penalized likelihood, which R has some support for. So for the single season occupancy model, there is a special form of the model that's fit with the fitting function occupen. And penalized occupancy can help handle these situations and also similar situations where you got separation related to covariate issues. But I would say that in many more cases, if you have very few detections and you're getting Hessian and optimization type problems, the unfortunate truth is that you probably just cannot fit occupancy models, and it would not be a good idea to try to extract more information from that data than you can realistically get. And in those cases, I would suggest dropping back to the detection naive equivalent model, which would be, for example, a logistic regression or some kind of count-based regression like a Poisson regression. And that is, of course, a problem in the sense that you're ignoring detection. But in my opinion, you might be making a much worse mistake trying to um, estimate parameters when you just simply don't have enough data to do it. I see there's another question. Can unmarked now handle the Richmond et al. 2010 conditional co-occurrence model? Uh, the short answer is no. It does support the Rhoda multi-species model, so just to briefly talk about this a bit, the Richmond model basically has a structure where you have one dominant species and one subordinate species, and the dominant species can affect both the detection and occupancy of the subordinate species, which could make a lot of sense in cases where you have like predator and prey relationships. And then you have the Rhoda type model, which doesn't have a direction in the effect, so it just has the species, there's no directionality in the interaction, um, which can be good in some cases. However, I actually have developed a draft version of the Richmond model or the similar, what's the other paper? I'm trying to remember the author's name. I apologize if you're listening, but there's another paper that fit almost the same model at almost the same time, Waddle et al. 2010. So I do actually have code for that model, which I have not implemented in the released version of Unmarked. So if you are interested in using that and I guess testing it out, then please reach out to me. I would eventually like that to get into Unmarked. It just hasn't been at the top of my priority list, but I would like to get it in there. Okay, so another question. There could be cases where a species is narrow ranged and sites are limited in nature, like in the case of a frog. So what's the best way to handle the small data set? I mean, that really depends on the specific experimental design. So, and really, it also depends a lot on what you're defining as a site, which I kind of alluded to at the beginning of my talk. So, even if the species is very limited in range, um, you could have a scenario where your sites represent also relatively small areas. And in that case, potentially you could have a lot of sites, even if the like geographic range of the species is small. But how realistic that is depends on your knowledge of the system. Of course, you're trying to define the sites such that you don't have species moving in between individuals moving in between the sites and so on. I do think that, if your species only exists in one rock formation on one island or whatever, realistically, you just can't use occupancy models. I mean, if it's so constrained that it's only at one site, what you would call a site, then you really don't even need to do occupancy modeling because you know where the species is. So I guess that's probably not a very satisfying answer, but I guess otherwise I would give the same advice as I gave earlier. Uh, Perhaps use penalized likelihood, although again, I think you might be getting yourself into more trouble than it's worth with that. Or just use a naive model that ignores detection, which might not be that big of an issue if you don't think um, detection, if you don't think there's a ton of variability in detection based on covariates, or if, you think detection's pretty close to one. Or if you're able to, you could design your study such in a way that you force detection to be one by simply uh, surveying it so exhaustively that, you don't need occupancy modeling. But again, I realize that's probably unsatisfying. Unfortunately, there's lots of scenarios in experimental design that we just can't fix with statistics, and we shouldn't try too hard to do that, or we might, you know, manufacture new problems. In the case of survey in the field, how do I determine sample size with power analysis, like understanding the role of local people in ecosystem protection? Well, I think basically, how do I determine? I mean, basically, you're going to want to try a bunch of different range of different sample sizes, right? And then make a plot like the one I made at the end of the power analysis section. But that, I guess, begs the question of, well, what sites, what sites should you pick to put into the power analysis? That's going to depend on what you think is tractable in the study system with the money that you have available and the time you have available. And that's just going to be based on your expert knowledge of the system and what's realistic. But probably you're going to have a scenario where you have a certain amount of time and money that you can spend, and you can either focus that on a very large number of sites that you visit only a couple times, or a smaller number of sites that you visit many times, or perhaps a number of sites that you visit multiple times and a bunch of sites that you only visit once, which actually occupancy models can't handle. And so basically you would just set up your experimental designs to capture that range of possible ways that you could break up um, your resources that you have available. And then I guess the next step would be to decide, well, you've got to choose some effect size, right? Which is pretty hard to decide. And so that's where your knowledge of the system and you thinking very hard and carefully about the problem is going to come in. I don't really have general advice for that other than to say, hopefully you can just get in your head like, well, it seems reasonable that if this cohort's having an effect, it should be shifting occupancy from some low number to some medium number. So you could say, what's the effect size that would cause a shift in occupancy from 25% to 50%, right? And then you kind of work backwards to get what the effect size would need to be to create that shift, and use that as your test effect size. And then, of course, you probably ought to be testing multiple different effect sizes to be most conservative in helping you decide. So in my example, I didn't vary effect size, but that's something you could also vary to look at in a power analysis. How would you define a successful detection in the context of your forecast skill metrics? I'm not sure I understand the question. Do either of you maybe understand? I mean, to me, a detection it depends on the type of study design that you have. Maybe it's just something I said that I phrased badly, but a detection is kind of an either or thing. Like either you detected it or you didn't. You could have errors in the detection process, I guess, in the sense of, and I guess that gets back a little bit to like the false positive issue I was saying earlier, where you've detected a species, but in reality you've misidentified it. And there are specific models to handle those, which Unmarked has very small amounts of support for. But otherwise, I'm not quite sure how I would answer that. So I apologize. If you want, you can feel free to email me with a more specific question.
Yeah. If you have more questions, feel free to email Ken. I think we are almost on time.
Yeah, so can you provide links for some books to look into, please? Yes, I could definitely do that. I'm not sure where
I
I think.
will. I've been keeping track of the books that you've mentioned and some of the papers, and so I will touch base with you after this, and before I send out my follow-up email next Monday to get those.
Okay,
And
great. Yeah.
make sure that to
Perfect.
get that sent out to everyone. And
Yeah.
yeah, just want to thank you, Ken. Really great presentation. Fun to see the references to some of the other packages and analyses that we've looked at. And
Yeah, huge thanks to all of them. So
yeah.